Hi everyone. So today we are going to have the problematic aspects of heat exchanger. Like in the last class, we have started analyzing the basics fundamentals of what heat exchangers are. We have tried to understand the classification of heat exchangers, the LMTD method, and why we are going to use this LMTD over analyzing the temperature difference in the heat exchanger, what are the types of heat exchangers are there, and how does the temperature distributions happens when a fluid flow within a heat exchanger. So all this accompanies the fundamentals or basics of analyzing, okay, what heat exchanger exactly is, how does it operates, and what technicalities does we face over there. So in today's class, we are going to have some problem aspects of heat exchanger, like how we are going to apply the fundamentals that we have studied and analyzed in our study. So we have discussed about logarithmic mean temperature difference for different types of heat exchangers. In today's class, let's have analyzing over how we are going to tackle this fundamental in our day-to-day life problems and how we are going to solve those problems. So let us start with some of the special cases to identify the logarithmic mean temperature difference in a heat exchanger. So in the special case, the first is the when the fluid is undergoing phase change. So here I want to make you a brief about the phase change processes. As we know, phase change takes place at constant pressure and temperature, isn't it? We have studied it from the basics law of thermodynamics. So as it takes place at constant pressure and temperature, if we will remember the TS diagram, then the phase change takes place within the dome, where delta T, that is the temperature at which the liquid it has saturation condition in the liquid phase, will be same as the temperature of the liquid when it is completely converted into its gaseous state. That is, the delta T will, the temperature will be same, the delta T will be 0, and the change in the temperature is because of the latent heat that comes across to play a role over here. So if one of the fluid is going phase change, then two equipments comes into picture. If you'll remember last class, then what we have studied, there are condenser and evaporator, in which phase change from liquid to gas and gas to liquid takes place for evaporator and condenser respectively. So let's analyze the case of condenser. So in the condenser, the flow either can be of parallel or counter. Let us take a case of the parallel flow and a counter flow. If we'll try to plot the temperature distribution, how it is going to be that in a condenser, the cold fluid, that temperature at the inlet and exit will be same, because phase change is taking place and phase change takes place at constant temperature. Then we are applying a colder fluid, and the fluid temperature changes from C1 Ci to Ce. Similarly, the phase change takes place for a counter flow condition or a counter current condition. We can see the temperature distribution will be this way: Thi, Tha, and Tci, Tc, that is opposite to the flow direction. Similarly, if we'll move on to a evaporator or a boiler type, then what we see is that the temperature of the liquid is directly converted to vapor. Condenser, vapor is being converted to liquid. Here liquid is being converted to vapor, so it is considered to be as the colder part, and the hot is heat is being flowed through a fluid. For example, let us take an example of flue gases. So if it is flue gases, then from the gases at high temperature, the heat can be transferred to the water, to which is at the saturation temperature condition, to convert it from the liquid state to gaseous state. So this is how the temperature distribution is going to look like. Then let us consider the case of this parallel flow. The logarithmic mean temperature difference can be delta Ti minus delta Te divided by ln del Ti by del T. Then for this condenser and parallel flow case, we can just expand it and we can write it at Thi minus Tci minus The minus Tc divided by ln Thi minus Tc by Thi minus Tci by Thi minus Tce. So here the phase change in condenser taking place, so Thi is equals to The. So in the numerator part, we can cancel out the Thi and Th, because it is in minus terms and it will get cancelled out. Then it is Tce minus Tci divided by ln Thi minus Tci by Thi minus Tce. Then let us move on to analyzing the counter current LMTD. So you remember the temperature distribution curve. THI, TH is there, then TCI, TCE, then del TI in the counter current will be THI minus TCE, and del TE will be THE minus TCI. So here for a counter current, by substituting the temperature conditions or temperature values over there, what we obtained is that the counter current LMTD is TCI minus TCE by ln THE minus TCE by THI minus TC. THI, so here I will substitute the THI equals to THI, so I will substitute THI is equals then THI minus TC by THE minus TCI. Then let's just make it upside down, then the negative term will be go there, and we can take this negative term within, then it will be TCE minus TCI divided by ln THI minus TCI by THE minus TC. So you can see that the logarithmic mean temperature difference for a counter current flow and for a parallel flow for a condenser is same. Same case will happen for evaporator also. So if a phase change is taking place, then you have been asked to find out the LMTD, then you can either find out the LMTD for a parallel flow or a counter current flow, and the LMTD for parallel flow or counter flow will remain same. There won't be much changes over there. Moving towards the second case, that is the case in which for a counter flow heat exchanger, if the heat capacity is same, that is the MCP is same, that means the MCP for the hot fluid is equals to MCP for the cold fluid. If we will be move along to analyze the energy balance equation between the heat transfer between the hot fluid and cold fluid, what we can write that MCPH THI minus TCE will be equals to MCPC TCE minus TCI. Here MCPH and MCPE are same, we will just cancel it out, then THI minus THE is equals to TCE minus TCI. So we can take it aside that THI minus TCE is equals to THE minus TCI. Let us consider the LMTD for a counter flow. Then it is this THI minus TCE minus THI minus TC. So this will be 0, and ln this thing ln these two are same, the numerator and denominator, then ln1 ln 1 is 0. So it is 0 by 0, that is the undeterministic form, and we know for the fundamentals of the derivative that if a equation or if a system comes to be in an undeterministic form, 0 by 0 or infinite by infinity, we try to go and apply there the L'Hopital's rule or L'Hopital's rule. That's primarily it is called, the H is silent over here. So as per the L'Hopital's rule, the LMTD of counter current heat exchanger for the same mass, same heat capacity will be either del Ti or del TE. That will be either of any these two temperature difference. So these are the two basic parts from which we face most of the problems in our GATE examination, and the 2 marks question is fixed from this section. That is, what will happen if a phase change is taking place in a system, or what will happen if in a counter current heat exchanger, if both the mass flow rates and the heat capacity are same for the hot fluid and cold fluid, how the LMTD is going to behave, and that we analyzed now. So now let us go and determine the area of heat exchanger by utilizing the fundamentals that we have studied till now. So for analyzing the heat exchanger area, if we will see, we know from the heat transfer equation we got that the heat flux is equals, heat transfer rate is equals to UA delta T LMTD. This means that this A is equals to Q divided by U delta T LMTD. How can we determine the Q? The Q can be determined from the energy balance equation. For the energy balance equation to be get it down, what all we need? We need the mass flow rate of both the hot fluid and cold fluid. We need the heat capacity of for the specific heat for the both the hot fluid and cold fluid, that is that we need the heat capacity. Then we have to know all the inlet and exit temperature of both the fluids. Then one more parameter that we have to know, that is the overall heat transfer coefficient U. So by keeping all these terminologies in mind, we can go and determine the area of a heat exchanger. So determining the area of heat exchanger, we can write the energy balance equation. From the energy balance equation, if any of the temperature is missing, then two equations are there, and one we can say that one equation is there and one unknown is there. We can solve it out. We can find out that particular temperature. By getting that particular temperature from this energy balance equation, we can go and we can determine the LMTD. And by getting the LMTD and getting the all the temperatures, will get the LMTD. From getting all the temperature, we can get the Q. The overall heat transfer coefficient is known to us. If it is not known to us, then we can determine it by the flow through pipe equations that we have analyzed. If it is laminar flow or turbulent flow, if it is laminar flow, from the Nusselt number, whether it is a uniform heat flux or constant void temperature, we can get it by 3.66 or 4.36. Or if it is a turbulent flow, we can determine it by the Dittus-Boltier equation. From this Dittus-Boltier equation and the dimension of the heat exchanger, we can determine the H value. By getting the H value, we will get the H, and we'll assume the H is equals to the overall heat transfer coefficient. If overall heat transfer coefficient is given, then that is very good for us. Else we have to determine it. Here one more question will come, that if overall heat transfer, to determine the heat transfer coefficient, we have to get the characteristic dimension. That is, if it is a tube, the diameter of the tube. And yes, we have to know that the diameter of the tube is given. If it is not given, then it would be quite difficult to apply those equations for the turbulent flow or the laminar flow condition to determine the HTC. So you have to be known, and if not known, the data would be sufficient to determine it from the equations as mentioned now. So from there we can calculate we calculated the Q value, we calculated the delta T value, we know the U value, then we can get the value of A from this equation, that is A equals to Q by U delta T LMTD, and this A will, for a heat exchanger, will be pi dl NP, where N is number of tubes and P is number of passes, L is the length and D is the diameter. Now we will move on towards analyzing the effectiveness of a heat exchanger. So what is the need of a heat exchanger? That is, if there is a system with us and we need to extract energy from there, then how effectively the device that we have designed is being capable to extract the energy from that instrument and transfer it to the ambient. So here it is signified, or it is identified by the terminology effectiveness of heat exchanger. Then effectiveness of a heat exchanger is a ratio of Q actual to Q maximum possible. Then what is Q actual? Q actual is mCp delta T. Okay, the Q actual is mCp delta T. What is mCp delta T? That is, either you have the hot fluid flowing or cold fluid flowing from the energy balance equation. You know the heat capacity of the fluid, you got the temperature difference between that, then you got that, okay, actually this amount of heat is being transferred from my hotter body, or heat is being absorbed by our colder body, and from there you determine, okay, this is my actual heat. Then we have to determine what is the maximum possible heat. So let us determine and analyze this maximum possible heat. So if I will say I am giving a maximum amount of my energy to a system, then that system will definitely undergo a phase change process, because phase change is the maximum sensible, means maximum energy if we deliver to a system, its molecular defragmentation takes place and it starts changing its phase, microstructure and phase. So if a phase change is taking place, will definitely takes place if we give the maximum possible heat transfer. If a phase change takes place, then the heat capacity tends to infinity, isn't it? Because the latent heat will come into picture over here, and we know that this Q is equals to mCp delta T. For phase change process, delta T will tends to 0, then this will be Q by delta T is equals to mCp. As delta T tends to 0, this term will tends to infinity. That means this mCp will tends to infinity. But for a practical case, the mCp can never be tend to infinity. So what will happen over here? For a maximum possible, we need to have the smallest of the heat capacity between both the fluids which we are encountering. and if we got the Q equals to mCp delta T, then if mCp is the smaller one we are considering and we need to have this as a higher one or maximum possible, the delta T should be the highest, isn't it? So if a flow is taking place, suppose two flows are there, THI, THE, TCI, TCE. Among these four temperature, the combination that will give us the maximum temperature difference is THI and TCI. THI is the highest possible temperature and TCI is the lowest possible temperature. So that difference is going to have the maximum value. So the maximum possible heat encounters the value of mCp small THI minus TCI. So by having their ratio, we can calculate the effectiveness to be mCp delta T by mCp small THI minus TCI. So here again two more cases comes into picture. The first case is that if suppose your mCp hot is less than mCp cold, then your effectiveness, I can write mCp delta T mCp hot THI minus TCE divided by mCp hot, because Q small, the Q maximum possible, we have to take the mCp small, mCph THI minus TCI. So mCph will get cancelled out. It is THI minus TCE by THI minus TCI. Similarly, if mCpc is less than mCph, I can take mCpc TCE minus TCI by mCpc THI minus TCI. So that will be TCE minus TCI by THI minus TCI. Okay. If in this case the mass flow rate and the specific heat is same for both the hot fluid and cold fluid, we can use either any of this equation that has been determined by us. So here also, if you know if a heat exchanger's effectiveness is given to you and you know any three of the temperature, you can determine another temperature of that of the fluid that is being driven in that heat exchanger. So with this we have come to analyze what effectiveness is. So in the convection heat transfer, we have come across towards a terminology that is the number of transfer unit. So if you will see NTU, then it is in the form of UA by MCP. So what is the unit of U? Is watt per meter square Kelvin, isn't it? Into meter square. What is MCP? Kg per second. What is CP? Joule per kg Kelvin. So here it will be kg will get cancelled. Joule per second is watt, that is equals to watt per meter square, then watt per Kelvin divided by watt per Kelvin, that is a non-dimensional number. So NTU is a non-dimensional constant factor that is shown by the ratio of UA by MCP. So if you multiply the U with A, what does it signifies? The overall heat transfer coefficient multiplied with the area, that is the rate of heat that is being transferred per unit temperature difference in a system to its heat capacity, is being shown by the number of transfer units of a given system. Then we will go on to analyze the capacity rate ratio, that is the ratio of MCP small to MCP large. If capacity rate ratio tends to 0 or equals to 0, what does that mean? Either of the process or either of the fluid is going a phase change process. If for system your capacity rate ratio is 0, that means the system is going a phase change process. Or if MCP small is equals to MCP larger, then C will equals to 1, that means 0 is less than C is less than 1 for a system. So this is the significance of NTU and capacity rate ratio. So here we will go and analyze that for any heat exchanger, the effectiveness is a function of its NTU and capacity rate ratio. For a parallel flow heat exchanger, the effectiveness will be 1 minus e to the power minus 1 plus c into NTU by 1 plus c. And for a counterflow heat exchanger, the effectiveness will be 1 minus e to the power minus 1 minus c into NTU by 1 minus c e to the power minus 1 minus c into NTU. So if you have to determine the effectiveness by using the temperature, and you know all the temperatures of the fluid that is flowing to the heat exchanger, you can directly calculate from the temperature ratio equation. If you know the NTU, then the effectiveness and the capacity ratio, then the effectiveness can be determined by this equation. Okay, here again another case comes into picture. What is that? Supposing if the phase change is happening in a heat exchanger, phase change is happening means my C will be 0. If my C becomes 0, you substitute the C over here, then this will be 1 minus e to the power minus NTU. Here it will also be 1 minus e to the power minus NTU. So for parallel flow or counter flow, the effectiveness will be 1 minus e to the power minus NTU. Supposing if your heat capacity is same, then for parallel flow, it will be 1 minus e to the power minus 2 NTU by 2. In the equation, you substitute C equals to 1, we will get this answer. But for a counter flow, if we will substitute C equals to 1, then that will be 1 minus e to the power some 0 something to the power 0 is 1, 1 minus 1 by 1 minus, so 1 minus 1. So if this is overally this 0 by 0, 0 by 0 again undeterministic form, so we have to apply the L'Hopital's rule, and by substituting the L'Hopital rules, it has been observed that the effectiveness comes to be NTU by 1 plus NTU. So these are the equations. So if in order to determine the temperature, if you know the energy balance equation, you can find it from there. If you know the NTU and capacity ratio, then you can calculate the effectiveness. From the effectiveness, you can calculate the temperature. Then from the temperature, you can calculate the area. So this NTU method is an effective way to determine the area of a heat exchanger. Now we will be going to analyze a very interesting term part of this heat exchanger, that is known as fouling. Okay, you have heard the term cavitation. So what cavitation is? Let's see, go through and analyze an example. So everyone have seen that we have a pipe we use in our garden. So in the pipe, what happens, that liquid flows. Then suddenly when we close the pipe, some of the liquid get trapped over here. Then when the temperature is higher, partial pressure of water vapor is means less, as it is not saturated with the partial pressure of vapor, then we observe that the water get evaporated and it's form a gaseous kind of thing on the surface. Then when the temperature falls, this evaporation will comes into the droplet of water particles. Then what happens, this give rise to a formation of some scaling on the surface. The same thing happens in a heat exchanger. When liquid passes through a heat exchanger, let it be a hot fluid, let it be a cold fluid, what happens, the fluid will carry some dirt in that will stick around the wall, and because of this pressure difference also, the evaporation and condensation will cause the formation of the scaling over it. So this forms a scale kind of structure or a layer of dirt that offers a resistance to the heat transfer from the surface of heat exchanger, so that becomes the lesser in the magnitude of the heat that is being exactly transferred in during the process, and this is known as the fouling of heat exchanger, and the scales that offers a thermal resistance to a system in which heat transfer is taking place. So with this, we have successfully concluded our subject of heat transfer. So in a heat transfer, we will have a brief discussion now, that we studied the modes of heat transfer. Here in the modes of heat transfer, we studied about the conduction. In the conduction, we studied about thermal conductivity. We studied about the 1D and 3D equation. We studied about the steady and unsteady heat conduction. We studied about the conduction through extended surface or fins. Then we moved on to the convection. In convection, we studied about the natural convection and forced convection. Then we moved on to the radiation part. Then we moved on to the heat exchanger portion, where we analyzed the all the classification of heat exchangers, the type, and the LMTD, NTU, and overall aspect, and we have studied some of the non-dimensional numbers. So in the upcoming classes, we will be solving the problems that has been encountered in the GATE examination from this subject, and while analyzing this problem, we will work refresh our or summarize our fundamentals by the help of the formulae, and once analyzing the formulae, we will try to solve the problems, and we will have a recapitulation of each section. Like in the first class, we'll try to solve the conduction problem, then in the conduction problem we'll have its equation. Initially we'll have all the formula discussion, then we will move on to its question solving part. Similarly, in the convection, we'll solve all the equations part. First we'll recapitulate that, then we'll try to solve the GATE question. Same for the radiation, and same for the heat exchanger. So in the next upcoming 2-3 classes, we'll try to solve most of the GATE previous year questions, so that we can have a clear aspect of what we have studied till now. So till now, if is there any kind of queries, please feel free to ask me, or you can refer the textbooks that has been mentioned in the first class of mine. And apart from that, if you have any query, please feel free to ask. You can, if there is any derivation in which you need more clarification, or there is any fundamental part that you have to analyze more, please let me know. We will definitely discuss it out, and we will try to solve all the problems, most of the problems definitely in this class. And apart from this problem, if any queries or problems is there that in clarification you need, you can feel free to ask me. Thank you and have a good day.